Hi, can you hear me?
Yes.
Hello? Okay, good. Anyhow, I don't think anyone else is coming, so I'll just start. Hello. Apparently, it's very cold. That's why we opened the door. Hopefully, it will get hot. All right. Any questions? Anybody? Questions? Some people are asking about bonus. Just pick the area you like, and you can do many examples. So if you like, what kind of physics do you like? No, the guy behind you. You mean, right? Oh, are you taking quantum? Okay, good. So like, no, I have no idea. But yes. Uh, yeah, right. So take a bunch of examples. Oh, like, oh, I know one for you. Springs. Apparently, the Karush Kuhn Tucker can be seen as a, so in the BV textbook, they do the spring example with Karush Kuhn Tucker. So you can put that in as well. But anyways, do as many examples as you want, as long as you fill 50 minutes. And don't talk slow. I can tell. Don't go like, and this is, no, you can't do that. Speak like you speak to your friend who is smart enough to understand the speed that you speak. All right. If there's no questions, today we'll just do examples. So I'll do questions that you will see in the midterm.
Can I quickly
like
ask
the
a
style,
question,
the first few computations.
Prof?
Also duality. I put a bunch of duality questions in the homework. I will put a duality question in the midterm, but I don't want it to be hard. I need to think. So, but we'll see. All right, so here are the KKT conditions. I put it in one slide like you asked me, so that you can just reference. So, yeah, so if X is a local minimum and regular means the constraints HI of X star and GI of X star for I 1 to whatever are Li, right? If that's the case, then oops. If that's let me backspace. Yeah. If that's the case, then the Lagrangian has a stationary point. So let me remind you, the Lagrangian is f plus summation of lambda I hi and summation of mu I gi, right? So it's just the long Lagrange multiplier, and it's a stationary point for it. And I didn't put a pause. So, and moreover, you have that the mu j coefficients for the inequality constraints are non-negative, and there's 0 for the inactive constraints. Okay, so that's how you find the candidates. So we will, in the example, we will first compute these two to find the local minima candidates. And then on the second step, I have to verify regular point, stationary, we already have it. This one, for active constraints, I also need it. And then I also need convexity. So I need this matrix to be positive definite on the tangent space. So to be clear, it doesn't have to be on the whole space. So for example, 2 minus 2, 0, 0, tested against 1, 0, and 1, 0 is equal to 2, which is positive, even though 2 minus 2 is, subtle. So it's not positive definite. Okay, questions? Wait, Daniel, can you hear me? You can't hear me? Okay, what's going on? Oh, okay, wait. So I thought I did this. Can you try again?
Testing.
Can you try? Daniel.
Testing.
What is Daniel, can you try? Okay, now I can hear you. Yes. Okay, thank you, Daniel, so much. Thank you. Good man. All right. Yeah, so let's do some examples. So as usual, I start with the simple one, and then we're gonna do one you're gonna see in the midterm. Okay, like a very long, disgusting one. Oh, I'll do it right now. Let me find it. Yeah, it should be there. Did you get it? What? You got it? What? It's right. Isn't this the file? Yeah, you found it, right? Okay, good. Yeah, that's the one. Yeah. All right. All right. So yeah, let's start with the simple example. So they ask you to minimize this guy over these three variables. Can someone tell me what's the constraint? Just to see. What is it? Yeah, thank you. So, and all right, let's start. So first you have to, we're looking for the candidates, okay? Because I don't know what the min is, so I'm searching for it. And how do I find it? I set the Lagrangian to 0. And if you do that, you get the following guy, okay? And if you set it to 0, what's the solution? I mean, you have the slides, so I don't know what the hell I'm talking about. But actually, I can ask you. Yeah, can you tell me from here what is x1 equal to? Just to see if you can read. Huh? Oh yeah, I was gonna say, yeah. So they're all equal to negative mu, yeah. So you split cases. Suppose your constraint is inactive, meaning that this inequality is strict. Then your mu guy is 0, and then your candidate is the origin. Can someone tell me why this is not a local minimum? Very good. Very, very good. This is equal to 3, which is positive. So it's not feasible. It's not in the constraint space. Okay, good. Now, suppose your constraint is active, then G of the minimizer will be 0. And we know that they're all equal to minus mu. So, but the constraint is active. So you plug it in. So you plug it in and you have, what do you have? You have G of minus mu is 0, which is just this guy, right? Is that okay? Yeah. Okay, good. And then you solve it for mu. You get mu to be 1. So you got a candidate. So as usual, I am not done. I have to verify the constraint and the Hessian. So let's do the Hessian. When you compute the second derivative of this guy, you get the identity. Can someone tell me why I get the identity? You have what? Yeah, okay, yeah, sure. Or you can see it from here. You have one guy, two guys, and it's just like, yeah. Okay, good. All right. This is always positive definite. So you have local min. All right. So x star equal to -1 -1 -1 is a local min. Can someone tell me why is it a regular point? Why I should have added that. So why is it regular? Huh? Perfect. So gradient of G at x star is first of all, what is gradient of G? Gradient of G is 1, 1, 1, right? Right? But this is always, and then plug in your constraint, which your minimizer, which doesn't matter, it's the same thing. And this guy is not 0, so it's Li. Okay? So let me go back to my conditions. So I have regular point, I have stationarity, I got my mu J to be 1, so I have the second guy. I don't have any inactive constraints, so this is trivially true, and I got positive definite. Okay, so please make sure you do this. Go like, okay, did I do this? Did I do this? And then you can say that your guy is a local minimum. Okay. So 5, how many? Yeah, 5 constraints. Okay. Does that make sense? Is that okay? Yeah. Okay, good. Everybody happy with this? That's the main thing. If there's one thing from today, I just want you to understand that this is what we want you to do. Just go like 1, 2, 3, 4, 5. Okay, now I'm going to do a disgusting example that I think I will put something related. Okay, this is a very long example, so don't kill me. You will have 2 hours, so you have plenty of time to do it. All right, so the function here is minimize x1, x2, given these 2 constraints. Okay, so these are the constraints. Any idea what the constraints look like? Yes, so what's the first one? Yeah, so this is one guy, and what about the other one? Yes. So, and it goes like this, as its radius 2, and it goes like this. Huh? Oh yeah, it is root 2. Yes, you're right. I can't compute. So this is 1 plus root 2. Yeah. So it would barely. So it's more like this. Yeah. So there is a feasible region. It's a priori is not obvious at all. And the feasible region, can someone tell me what's the feasible region? Yeah. Yeah, so the first guy says, take all the guys inside. The other guy says, take all the stuff outside. So the common part is this blue stuff. Okay? Everybody happy? So make sure you draw your feasible region, because when you're looking for the candidates, you can just stare at your picture and tell us, this point is not in the feasible region, so I'm done. You don't have to like check Hessian and all that stuff. Okay, good. All right. Well, too many constraints. Okay, whatever. So I compute the Lagrangian of this whole thing, and it gives me this beautiful system. Okay. Yeah, fun times. So this is the one. Is that okay? Any mistakes? You can let me know. So from here, if you're a genius, you can probably solve it directly. But for me, it takes some time. So I have to go over all the constraints, all the possibilities, active, not active. And by that, I mean mu1, mu2, not 0, and mu1, 0, and mu2, 0. Okay, these are the 3 cases. Okay. All right. I don't know what this picture is. All right. Case 1. Case 1, I should put more pauses. Gee. So if both of them are active, meaning mu1 and mu2 are strictly positive. Okay, I mean, let me just say this. If both of them are, I should say something else here, because sometimes there's 0. Sorry, let me fix this. So by this, I mean case 1 would be both active. So G1 of X star is equal to G2 of X star equal to 0. Case 2 is what? Only G1 is active. G1 of X star is 0, and G2 of X star is strictly negative. And case 3, G1 of X star, G2 of X star equal to 0. All right? You don't have to write this. You can just say case 1. You can say active 1, inactive 2. Okay, don't do this. This is pedagogical. Okay. If both of them are active, you have, they're both equal to 0, meaning your minimizer somehow gets hit with both. Okay. Are you guys following? I'm not sure. So silent. Is that okay so far? Besides being rude? All right. So if you just look at this system, you have 2 equations, 2 unknowns, and if you solve it, you get this solution, 2, 1. Okay, so I wrote down my system and I did some cancellations, and it was pretty easy because they both have x minus 1. So I just added the 2 equations. So it was very easy. And I got the solution 2, 1. So this is the only intersection over here, 2, 1. Okay. And then I plug it into my Lagrangian. So I get this system, and then you have 2 equations, 2 unknowns, you solve it, you get mu1 0 and mu2 1/2. Can someone tell me why 2, 1 is not a local minimum? Not you. Anybody else? Does anybody know why this 2, 1 will not be a local minimum? I'm gonna wait till someone says it, so it's not really just me talking to Ben Roy. Anybody? Zoom people? Daniel, do you know? Daniel. Hello? Daniel, are you there? Yeah, what do you think? Can you tell me why 2, 1 will not be a constraint, minimizer? Jesus, okay, fine. It will not be a minimizer because, what? So so what's the mistake exactly? They're both active, so what? Mu what? No, sorry, yes, go ahead. No. You can have equal to 0 because they're both active here. So does anybody know? If you stare at the conditions, one of the conditions is that for active constraints, is that what you meant? Yeah, okay, good, yeah. So mu1 is 0, even though G1 is active. So this constraint failed. That's all. So where are we? Yeah, so no, because mu1 is 0, even though G1 is active. Okay. All right. Oh my God, too quick. Suppose case 2, only G1 is active. G1 being active means G1 of X star is 0. And it also means that mu2 is 0. Okay, so then you have the system and they're both equal, so that you get x1, x2 is equal to 2 mu, or 1 over 2 mu1 plus 1. You plug it in into your active constraint, and you obtain that mu1 has to be 1 over square root 2. Okay, so this is the, so this, from here you get the candidate, I wrote it somewhere, I don't remember. So you get square root 2, you get 1 over square root 2 plus 1, 1 over square root 2 plus 1. This is a candidate for local min, and in fact, I'll prove it that it is the local min contained in the feasible region. Okay, good. I do the last case to see if it gives me anything. Suppose that G2 is active, it means that mu1 is strictly positive. That's what I need, and it tells me that mu1 is 0. Okay, since mu1 is 0, I go back to my stationary equation. So I get x1 minus 1 is x2. Plug it in into your active constraint, and you get your two candidates for minimizers. So can someone tell me why the 0 minus 1 failed? It's the same reason you said a few seconds ago. Yes, good. So it has to be strictly negative. Yeah. And so from here, we get the candidate x star 2, 1 with mu2 equal to 1/2. Okay. All right. Okay. Now I found my candidates. My candidates are the following. This guy with mu1 being 1 over square root 2 and 0. And this guy, 2, 1 with Lagrange multipliers 0 1/2. Do you understand? If you have a question, just tell me now because we have plenty of time. So I'm not rushing. This is basically a review session for Wednesday. All right. So now I have my candidates. Now I need to verify them. So let's verify the candidates. We start with the case 2 guy, and again, go back to your slide on Kkk conditions. I need regular. Well, the gradient is this guy, which is not 0, so it is Li. Okay, and then you have to compute your Hessian, and your Hessian is just this matrix, which is a positive definite, right? What are the eigenvalues of this matrix? Anybody? And so boring. Any idea what they are? Yes. What is it? Yeah, I mean, I guess I don't know how you want to see it, but yeah, because I mean, I'm in for the whole thing. So square root 2 eigenvalues, lambda 1, lambda 2. Yeah, yes. Now I do the next case 3, where I had another candidate. Again, this guy is regular, but then when you compute the Hessian, I get negative definite. Okay. So if I ask you give me the maximum, this is the maximum. Okay, because the Hessian goes the other way. Do you understand? Huh? Okay, good. All right. All right, sure. Even though we were done for case 2, let's compute the tangent space so that you are comfortable doing that. The tangent space is given by the guys who are normal to your constraint. The gradient is equal to square root 2 square root 2. You dot it with V, so you get the system V1 plus V2 equals 0. And this has the solution 1 minus 1. Okay. Man, I want to ask you some questions. It's so boring. I'm bored. Okay, so okay, good. And then now suppose that it happened like in the midterm, I hope. I will try to find this. Suppose your Hessian looks like this, so 1, 0, 0, 0. When you test it against tangent vectors, 1 minus 1, you get it to be equal to 1. So even though 1, 0, 0, 0 is semi-definite, it is a positive definite on the tangent space. Do you understand? So, yes, yes. What's the what? How do I get what? Yes, perfect. So, so the question is, which solutions are for this system? Yeah, I'm explaining. So the question is how to solve this system, and if you solve that system, it's basically square root 2 dotted with V1, V2, and this gives you square root V1 plus square root V2 equal to 0. And yeah, okay. Good question. Yes, please ask me questions. It gets like boring. Okay. Yes. Should it be what? Okay, you're saying from the picture or what? Huh? Let's do it again. You're probably right. So the thing is this guy minus 1. I mean equal to 1, and then same guy equal to 2, right? So this is the system. You're probably right. There's probably some plus minus. I was too lazy to. So you take the difference and you get x2 squared minus x2 squared minus 1 squared equal to 1. Is that okay? Then I opened it up. What did I do wrong? So x2 squared. So one second, let me write it out. So it will be minus 2x2 plus 1. So then it will be plus minus. So this cancel out, right? And then the 2 goes on the left. So you have x2 equal to 2, right? Oh, but then when I plug it in, you're right. Thank you. But when I plug it into the other guy, x1 has to be plus minus. Thank you so much. So I plug it in, and I get this guy equal 1. And from here, I get x1 is, so I get plus minus, yes. So I get 2 and 0. Thank you. Oh, which I already, okay, no, I have to go back. Okay, let me do it now. So, right, but then, oh yeah, I think we are lucky with this. Okay, let me see. So, So yes, so you also get 2, 0. No, 0, 1. Okay, so what should I do? Maybe I'll do it here. Yeah, so let me verify or disprove 0, 1. Okay, what is my Hessian? My Hessian is what's my Hessian? I'll do it underneath. So I have to do case 1 over here. Okay. So first I have to compute the Hessian, which is mu 1 2 2 plus mu 2. But wait, didn't we disprove this? No, no, but oh no, I have to let me think. Oh, I have to do the stationarity first. Yes. So first I have to do the stationarity before I do this stuff. I have to check whether it gives me contradictory mu. So here I have to plug in 0 and 1. If you plug in here 0 and 1, you get 1, 1 plus mu 1. And then you get minus 2, 2, right? And then this is 2, one sec. So this is 2, right? And this is minus 2. And then this guy is minus 2, and this guy is 2, right? Oh, yeah. It's 1 minus 1. That's right. Okay. Is that okay? Now, let's check. We might be lucky. So the first equation, which equation is easy? Second one. So it says 1 minus 2 mu 2 is 0. So you get mu 2 is a half. And mu 1, and the other one is 1 minus 2 mu 1 plus 2 mu 2, so 2 over 2 is 0. I'm going to type it as well because I missed it. So, but let's just do it together. So mu 2 is a half, and is it 0? What? So you get 1. Yeah, so mu 1 is 1, right? Okay, good. So that doesn't break. Oh, it might be a very interesting point. It might be a minimum. It looks like a minimum from the picture. Yeah, like you see, I didn't even listen to my advice. You listened to my advice. That's very good. Okay, the Hessian. So this is mu 1. So now we're verifying the point 0, 1 with 1 with mu equal to 1.5, and then this is 1, and then this matrix was 2, 2, right? Yeah, so this is 2, 2, 0, 0. And then the other guy is minus 2, minus 2, right? Okay, good. This looks disgusting, but I think it's okay. So it will just be the matrix 1, 1, right? Which is positive definite. So yes, the long way, yes. So yes, 0, 1 is a local min. Or you can just look at the picture, like smart people do, not me. I'm semi-smart, not fully. Okay, I try. Right, is that okay? Thank you. Does that make sense? Yeah, I'll type it as well. That was nice. So what else? Yeah, okay, fine. You know what? I might as well compute the tangent space for you, and I will type it, but I want you to have it here. So I have to give you the tangent space. So gradient of G1 at 0, 1, and gradient of G2 at 0, 1. Okay, so what is gradient of G1? So I have to plug in 0 and 1. So I get the same thing. So we had it from before. What was it? Right, negative 2, 0, yes. And then what was the other one? And now I need to find all the V. So T star would be all the V perpendicular to both. Very good. So I need the following two equations: minus 2V1 to be 0, and 2V1 minus 2V2 to be 0. So I just get the 0 vector. Oh, right? Okay. I don't make it. That's what it said. So it's, yeah, it's trivially positive definite. And the tangent space, even if your guide was not positive definite, your tangent space is trivial. So it will work anyhow. All right. Okay. So that was the example. All right. It took us like 20 minutes with mistakes. So if you have questions, let me know, because that's the main material, okay, for the midterm. So you have to let me know if something doesn't make sense. I have to know ASAP. Okay. Here's another example. I will leave that to you. So now, because I will also put duality, like a small question. So let me, in the remaining time, go over that. Okay. Zoom people, if you have a question, I'm here. Last week we talked about the dual problem. That is basically, you start with some constraints and then you define the following Lagrange multiplier function. So this is the infimum of the Lagrange dual, x lambda mu, okay? And this guy here is called Lagrange dual inside. We talked about last time that this function in lambda gives you a lower bound for the minimizer. Okay, so G lambda, lower bounds minimum of f of x, and x in the constraint space. Okay, and the dual problem is the following: maximum of G lambda. Okay, given some constraints, and when this guy is equal to the minimum of f of x, it's called a strong duality. Okay, this is strong duality. And the difference is called the duality gap. Okay, so first I want to do an example where there's a gap. So this is the primal problem, e to the minus x, which looks like this. And you constrained with this set, which is basically the y-axis. But so if you stare at this, this is basically saying x is 0. So it's a very stupid problem, but it's still an optimization problem. And it's also a convex problem. So if you stare at it, the only way this expression can be true, I think it's equal here, yeah, is when x squared can be x squared 0. All right, let's start. So first I give you the dual function. What do? You put in your function and then you multiply your constraint by lambda, okay? And any idea what the function is? So when lambda is, let's say, which one is easy? Yeah, suppose lambda is negative. Okay, so suppose this is e to the minus x squared y, and you take an infimum x and y. Any idea what this equals to? Huh? What happens is you infimum, right? So how small can it be? Is there any lower bound? It's minus infinity because there's a minus here, and x squared can be any number. Is that okay? So it's x squared over y. Yeah, so you can take x to be really, really big. So then minus of x squared y would be very, very negative. Do you understand? Okay, my question is a calculus question. What is the minimum of e to the minus x squared over y for x in the real numbers? There's no optimization here. This is just calculus. And take y to be positive. Huh? Because why? Yeah. Right? Whereas if you go the other way, this guy goes up. So as x goes to minus infinity, e to the minus x goes to plus infinity. But you don't want that. You want minimum. And exponential beats polynomial, right? So that's why e minus x squared y still goes to plus infinity. You understand? Is that okay? Okay, good. Anyhow. So one is minus infinity, and when lambda is positive, what do you think? The stupidest answer. It's one, because this guy is smallest when x is 0, for lambda positive, right? Is that okay? Is that okay? A little bit? So. Anyway, and then this is when this guy is the smallest, and this is when, same thing, smallest. So this is the primal, the function. So 1 and minus infinity. Okay, so. Oh yeah, it is 0, yes. Wait, what? Yes. So that's right. What do I want to say? No, you're right. This is 0 because, thank you. Because take y to plus infinity, then lambda positive x squared y goes to 0. That's good. And then you're left with infimum x in the reals of e to the minus x, which is smallest at plus infinity.
Don't you have an issue with x going to infinity and y
No,
going?
you have two infimum, and you first take the infimum over y. So when you take the infimum over y, so let me do it on the side. So the question is very simple. Find the infimum of e to the minus x plus 1, x squared y. X is a real number, y is positive. By linearity, you bring in the infimum of y. Okay? Is that okay? Yeah? I don't understand. So the variables are separated, so I can bring in the infimum. This guy does not depend on y. So, and then exactly like you said, this is the smallest when it goes to plus infinity. So it's 0. Okay? Yeah. All right, good. And then for the other one, the infimum is attained at 0, at the plus infinity. All right, good. Let me finish up here. So here's the amazing result. This is equal to 1, and the maximum of this is equal to 0. Okay? So the dual gap P star minus D star is equal to a minimum of E minus X minus maximum of G lambda. So it's equal to 1. Okay? That shows you that the dual problem is not always optimal. You can have gaps. Okay, so it doesn't always work. All right, but it works when the following are true. Hopefully you remember them. We talked about them half an hour ago. The KKT conditions. If you have these conditions, then in fact you have strong duality. So I'm going to do this and then we're done. So the KKT conditions tell you that the Lagrange dual has a stationary point at x star, and because of the positive definite, the convexity, this is the minimizer. So let's stare at the next calculation. It says that that this guy over here on the left is equal to maximum of G lambda, and this guy is equal to minimum of f of x. Why are these two 0? Any ideas? Why did they die out? So this guy dies out because this is your constraint. And this guy dies out because of the following. When gx star is 0, mu I is strictly positive, so they're dead. When g of x star is inactive, mu I is 0. So in either case, the product is 0. Okay? This is the KKT conditions. So what I proved very quickly was that if you have KKT, you have strong duality. Okay? So we will give you a problem, you find the dual, you check KKT, and then you say that the solutions are equal because of KKT. Is that okay? All right, good. Oh, because this is a, so first of all, this guy is equal to the infimum of the L guy. right? And yeah, so this is, and then this was what we call the G lambda. And because of you have stationarity, you can also take the maximum. So, so the question is, again, this guy is the infimum, right? Over X, right? And that was our definition of G lambda mu, right? Is that okay? Okay, I don't know. I mean, yeah, right. So by KKT, we have this condition, right? And we also have that it's positive definite. So it's a minimizer for L. Is that okay? Yeah. Is the last one? Right, but I want to have a review session. Not in person, no, on Zoom, whoever wants to come. Because the test is on Wednesday, right? Yes, when should I have the review? Monday? So that you have time to study. Tuesday, the day before, Monday, Thursday, the test is on Wednesday. I can do it after, like, wasn't that a nice test? What you mean, today? Saturday? What? Sunday? Yeah, but when to have the session? When do you want it, huh? Yeah, whatever, but tell me what you guys make the effort to come here, so you have first dibs, huh? Yeah, so I'll usually have it at 8 to 9. Yeah, but when? Monday? Monday, right? Okay, good. People told me to do 5 to 6. But then I will have multiple parts. Do you want multiple parts or more questions? Because multiple parts means you have carryover, you lose marks by carry. If you have a gradient that's wrong, the hairpin will be wrong. More questions, right? Yeah, that's right. I have no idea. No. But the computation will be there, the one we did today. Make sure you understand it, because I'm going to put a very similar one. And it will be worth like a lot of marks, because I know it takes a long time. Yeah. Oh, because it's not continuous. Might not be. It could be like infinity. It could be minus infinity. Yeah, that doesn't mean. I mean, I don't know. Maybe you're right. Yeah, maybe you're right. No, but you could be positive definite and like and go to minus infinity, no? With like isn't log of x? No, log of x is concave. No, but this positive definite is locally. It's not global. It's only around x star. I was gonna say, you see this example? What? No, but anyhow, this is like KKT, but applied in physics. Yeah. It's the convex optimization. It's one of the. Yeah. Yeah. So it fails the KKT condition. Yeah. But you fail the condition. Like this, mu1 is 0. Like this is a theorem we proved that in order to have strict local minimum, you need to have this guy to be strictly positive. No, it cannot equal 0. And the reason is we remember that equation we had mu j jj equal to 0. Yeah, it's the same thing. So yeah, they can both be 0, but we're talking about. I'm not talking about finding the candidates. I'm saying verifying. So you see this example. Because I didn't have time to do it. So this example over here, if you sit down and do it, you will get that it's not a local minimum, and mu1 is 0 for the active constraint. So this is in the textbook by the checkers. This is exactly your. You know what? Can we go to the? Let me show you because you have a good question. So if you go to the book on. You see here, this example. So you see this condition 354 is the one I talked about, right? J is strictly positive, and it says that. So in this example, if you sit down and do it, you get mu j to be 0, and 0, 0 is not a local. I didn't do this example. I was going to do it. Okay, let's see it. So, example 1. Okay. Okay. Yeah, mu2 is 0. That's right. Yeah, so you not you cannot use the theorem. So you cannot use the theorem that this can be a local min. So so what did we do? So we check this. Oh, I see. No, you're right. I should talk about it. I will add a correction. So yeah, so it fails the. You're right. It fails the. Yeah. So I will make a correction. You're right. No, I made a mistake. I'm not allowed to apply the result because this is 0. Yeah, in fact, you might be able to see it. So if I take x to be large, no, the theorem is correct. It's just, yeah, I have to, I don't know where I took this example from. I have to look for it. This is not my example. I don't know where I took it from. Yeah, this is not my. I mean, the theorem is correct. Yeah. I mean, the theorem. Yeah. So it's a strict local minimum. Look at the textbook. You see, even in the book, right? Same thing. Well, let me read the proof because you might be right. I want to see. So you might be correct. Yeah, okay. I think I understand. Yeah, I mean, in the example, I'm using a different theorem. Um, um, yeah, I will mention it. So they're both right. So if this guy is zero, you need positive definite on this strongly active tangent space. Yeah, so, and this is what the book says. So the book says, if you read it carefully, it says you might have degenerate. So meaning that you have active but zero. Then this is the theorem. You need positive definite on the tangent space of this case. So I will actually I have too much. All I needed was this kind of positive definite on this space. I don't need all the active ones, but no zero means it. So the book is the other textbook, the theorem is not from too much. You just need this for the positive definite, not for the positive. Huh? Yeah, let me look at so the book says, you see, like, he's asking this guy to be strictly positive for huh? Yeah. Yeah, these are the active constraints. So he's asking more than what you need. So the theorem in the other book is weaker. It says you don't need this. You only need this guy to be this on this. Like the example one, you got it? So this is is asking way more. The correct one that you should follow is the one from the book, where he allows it to be zero. He's asking his product, but then on positive determinant on the strongly active. Yeah. With what? Oh, yeah, I have to type this entire example. So, oh, you mean example one? Oh, no, case one. So I have to retype this. So yeah, now this would be, yeah, ignore this part, yeah. So I ignore it and I look for positive definite on this guy. What? Yeah, not the Lagrangian, the Hessian of the Lagrangian. Yeah. So I have to find the guys that are normal. I mean, we might have done this. So this point is, I think we did this, didn't we? So what is it? So it was 2-1, and then oh, so it's the same matrix because U1 was 0, right? Yeah. So it's not a local maximum. Yeah, we did, and it's not positive definite. Yeah, we ignored the U1 equals 0, and then I mean, if mu2 was 0, then we just look at that. Yes. Yes. Huh? So that mu1 is 0. Yeah. Oh, I see. So no. But be careful. Here we were lucky. This guy is negative definite. But we're asking, what if it was 2 minus 2? Right? Then we don't know. And you have to check the text for double space. So we're checking the very